Here we're going to cover types of covalent bonds. Now, you've probably heard that bonds can be single bonds, double bonds, or triple bonds. Carbon is a great example of an element that can do all three. Carbon can make single bonds, double bonds, triple bonds. Carbon can do it all. Now, a single bond just means that you're sharing two electrons, or we might say there's one pair of electrons being shared. A double bond means that there are two pairs of electrons, or four total electrons being shared. And a triple bond is three pairs of electrons being shared, or six total electrons shared between two atoms. How do you predict whether there's going to be a single bond, double bond, triple bond? You just start drawing it. I know in the end, I can at least kind of hint, like there are times when I can predict what might be likely for a particular atom, but at some point you just got to start drawing them. So for example, here in number 15, they want us to draw some Lewis structures, or sometimes they're just called electron dot structures. We've got bromine and iodine bonding together in A. And so you just start drawing the dots. Bromine, it's a halogen. 1, 2, 3, 4, 5, 6, 7. And then iodine is also a halogen. Iodine. Oh, it's also going to have 7 valence electrons. So I'm going to kind of purposely put the single electron toward the middle. So there's 1, 2, 3, 4, 5, 6, 7. I'll kind of purposely put it so that the single dots are toward the middle, and then we can link them up. Single bond. I'll tell you this much. Halogens and hydrogen are single bonds for life. Hydrogen and halogens. Because think about it. The halogens already have 7 valence electrons. They want 8. They want 1 more. So they're only going to make a single bond. So I'm never going to do anything wacky to a halogen like double bond or triple bond. They only need 1 more single bond. Same thing with hydrogen. Hydrogen's only got 1 valence electron, but he only wants 2. Hydrogen is a single bond forever. For example, CH4. So the central carbon has 4 valence electrons. And then I've got 4 hydrogen. Perfect. Carbon needs 4 more bonds. And now here I can hook on my 4 hydrogen. I'll purposely line up the 1 single valence electron on hydrogen so that it matches with the single electron on carbon. And then I can bond 1, 2, 3, 4. Hydrogen and halogens, single bonds forever. They only need to make 1 bond. But now when you get to somebody like carbon, anything is possible. And it just kind of depends on what you've got to bond with your carbon. Carbon needs 4 bonds. So carbon could do 4 single bonds. Or it could do a combination. I could do 2 double bonds. 2 double bonds will give me a total of 4 bonds. And if you think every bond involves 2 electrons, well, yeah, then 2 double bonds would be 4 and 4 for 8. You could do a double bond and 2 single bonds. That would give me 4 bonds for 8 electrons. Carbon can do a triple bond and 1 single bond. That would add up to 4 bonds, or 8 valence electrons. So somebody like carbon, you can play with a little more. Carbon can take 4 bonds. And so it could be a combination of single bonds, double bonds, and triple bonds. But then other elements are a little more predictable, like hydrogen and halogens. Single bonds forever. Okay, so here's a couple examples. They want us to draw nitrogen, N2, and this HOCl molecule. Okay, so with both I start by drawing the central atom, which in something like N2, there is really no central atom if you only have 2 atoms. So you think about drawing a nitrogen. Now, often when I draw a nitrogen, I start by putting my dots like 1, 2, 3, 4, 5. Usually I put my pair on the top and then I have my singles on the other sides. Nitrogen has 5 valence electrons. But now when I think about 2 nitrogen, I kind of want to draw my single dots so that they line up with each other. The single dots are where the bond is going to happen, right? And so now when I have 2 nitrogen atoms, I'm going to draw them kind of like this, where I can move that pair. I don't have to put it on the top. Well, I want the single dots to match up with each other nice and easy so that I can easily see where the bond is going to go. And so we're going to put the pairs on the outside, and then the 3 singles can line up toward the center. Okay, so let's focus on this N2. So then the next thing it says is determine how many electrons each atom needs. Well, 3 more, right? There's already 5 valence electrons. We're going for 8. So each nitrogen is going to need to make 3 bonds. We already kind of mentioned that there's no central atom because there's only 2 atoms. So now I can kind of pair up those 3 single sets of electrons. And if I were doing this with the dots, I would kind of think of it like this. I'd have my pair on the outside, my 1, 2, 3 single dots toward the middle, and then I do the same thing with the other nitrogen. But it's like a mirror image. I'm putting my pair on the outside, and then 1, 2, get out of there. 3 toward the middle. Now, in this first model, they're kind of showing like 6 dots toward the center, which is fine. There's nothing wrong with it. But I usually just do this connect the dot thing. 1, 2, 3. And so I'm showing that there are 3 bonds then between the 2 nitrogen. It's a triple. Each nitrogen needs 3 more bonds, so they'll just bond to each other 3 times. I can pair up all 3 of those single dots. And now each nitrogen has a share of 8 valence electrons. There's 2 electrons that are non-bonding, and then there's 6 electrons in the bond. Now, as you get better with these and you just take more practice, and if you get to the point where you're like, oh yeah, I totally get this, and I've drawn N2 18 times and I just know it's a triple bond, well then it's totally fine to do this. I mean, if you know that there are 3 single dots and you're just going to bond all 3, then you can just go dash, 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 and that would represent a triple bond. And we just have to know, like, whenever we see these structures and I see a dash, that represents 2 electrons being shared. So if I see 3 dashes, that's a triple bond. That involves the sharing of 6 total electrons. But drawing it like this is 1 bazillion% correct. There's nothing wrong with it. And then finally, if you're ever unsure of your structure, there are 2 rules of an acceptable dot structure. Rule number 1, everyone that wants an octet gets an octet. So like your nitrogen needs an octet, he's got to have it. And so we said, yep, each nitrogen has 2 non-bonding electrons and 6 bonding electrons. The electrons that are shared count for both. So yep, nitrogen both have an octet. Then the second rule is that you only have a certain number of valence electrons to play with. So if you add up the number of valence electrons for all the atoms in your structure, then that's the number of dots that you can draw. So if I have 5 valence electrons on each nitrogen, I've got a total of 10 valence electrons that I can distribute in a way that gives both atoms a full octet. There we go, triple bond, which kind of makes sense. So when I'm dealing with elements in the nitrogen family, they typically take 3 bonds. If they've already got 5 valence electrons, and they're looking for 8. So I can get creative with nitrogen, and that would be anything in the nitrogen family, nitrogen, phosphorus, arsenic. So with 3 bonds, you could do a triple. Nitrogen could do maybe a double and a single, or 3 singles. But yeah, with nitrogen, I start thinking, yeah, a triple bond might be an option. Kind of like the carbon family. When they make 4 bonds, you could have a triple and a single, And here, yeah, with nitrogen, I could do it just one triple, or I could do like a double and a single or 3 singles. Those are kind of my options with nitrogen or anything in that family with 5 valence electrons. Okay, so let's go back to particle B then, HOCl. Now, often we've said if you only have one atom of something, put that in the middle. Well, here we only have one atom of hydrogen, oxygen, and chlorine. So then it's like, well, which one goes down first? Well, then it's always going to be the atom that makes the most bonds. Often in the formula, it's probably written in that order, HOCl, and that's exactly how I would organize my elements. I mean, like down here, they just got the dots shown, but I would have probably put my oxygen in the middle. I would put my oxygen down first. Oxygen has 6 valence electrons, so you can organize them however you want, as long as you've got 2 pairs and 2 singles. 2 pairs and 2 singles. Oh, well then I kind of see that I've got room for 2 bonds, and I've got 2 things to hook on. One of them is a hydrogen with his 1 valence electron. You can put it wherever you want. You can put it on the top, on the bottom, it doesn't matter. And then, boop, there's his 1. I'll line it up with one of the single electrons on oxygen. And then I've got a chlorine. So I'll put the chlorine over by the other single dot. So chlorine's got 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Cool. And then I can link up by all the single dots. So I can link them up once. I can link them up twice. And there you have it, HOCl. So the hydrogen and the chlorine needed 1 bond. They needed 1 more electron to fill their outer shell. Oxygen needed 2 more bonds or 2 more electrons to fill the outer shell. Oxygen went in the middle because it can make the most bonds. So like for example, you can't, if I just look at this, the way that they've got the electrons kind of drawn out with the dots, you can't put chlorine in the middle, right? I mean, you could link up, like if I took these little plus signs out, you could link up these guys. Boop. I could connect the dots between hydrogen and chlorine. They each want 1 more bond. But then how would you bond chlorine then to the oxygen? If you put chlorine in the middle, he's full. He can't take any more bonds. So hydrogen and halogens will never ever be your central atom. They only make 1 bond, so they're always going to go on the outside. The central atom is often going to be the atom that can make the most bonds, which here would have to be the oxygen. And so then we sketched it out. And again, how you draw this on paper might look a little bit different. Here was mine. I mean, here's what they've got drawn. But these are 3-dimensional structures. And if I were really holding this hypochlorous acid molecule in my hand, I can twist and turn it in different ways. I mean, if I took this molecule that I had drawn with the green, and I just like, zoop, if I kind of like quarter turn it, I could turn it so that oxygen is on the bottom. I could flip it. I can make it upside down and backwards. And you can move these molecules in real life. A proper Lewis dot structure has to follow 2 rules. Rule number 1, everyone's got a full outer shell. Oxygen's got a full outer shell. He's got 4 non-bonding electrons and 4 bonding. Hydrogen only needed 2. And chlorine, yep, he's got a full octet with 8. He just needed 1 more. So that was rule number 1. Everybody gets a full outer shell. And then rule number 2 is just that you've used the correct number of electrons. So hydrogen provides 1 valence electron, the chlorine has 7, the oxygen has 6 for a total of 14. So you have to use 14 electrons and distribute them in a way that everybody gets their full outer shell. But how you draw it on paper doesn't really matter because you're drawing a 3-dimensional structure. And so if you're comparing with somebody else and you're like, oh my gosh, our structures look way different, it could be totally fine. Be totally fine. And again, I mean, some people would have drawn their oxygen differently in the middle. If you would have drawn your oxygen And you could do like 1, 2, 3, 4, 5, 6. On paper, that would be okay. And then you could put the hydrogen and chlorine by the single dots. And you could put your single dots, you know, like on the top and on the side. But either way, you're going to show the same like general structure. When you break it down, you're going to have an oxygen in the middle. That oxygen is going to have 2 lone pairs and 2 bonding pairs. Then on the outside, you're going to have a hydrogen somewhere with 1 bonding pair of electrons. And you're going to have a chlorine on the outside with 1 bonding pair and 3 non-bonding pairs. The bones of the structure are going to be the same no matter how you arrange them on paper.